I am Devdatta Basu, pursuing my Masters in Electrical Engineering Department under the guidance of Professor Balaji Srinivasan. Today, I will talk about how to maintain high purity structured light in an optical system by transverse phase correction. Conventional telecom is saturated with single mode fiber, and researchers are exploring how to pack more information in multimode of a few mode fiber. Unfortunately, this approach is limited by the crosstalk between those modes. Light processing orbital angular momentum, in short OM, offers a viable alternative to address the crosstalk issue. Such OM modes are characterized by an azimuthally varying phase with an intensity null at the center, corresponding to the phase singularity. Light beams with OM are also useful in high-resolution microscopy, quantum information systems, and sensing. Several techniques have been explored in the literature to generating these OM modes, of which special light modulator is most common. However, achieving high-purity OM mode is a challenge due to aberration in the optical system and non-ideal SLM performance. In our work, we demonstrated an idea to quantify the aberration and also determine the optimal configuration for compensating at the same to generate high purity OM. We need to extract the phase to find out the aberration from the camera image. It's difficult to extract the phase information because of many other features. We have used a GS algorithm to retrieve the phase of the CCD image by converging the RMSE value between the CCD and retrieved image, which should be lower than the threshold value. After retrieving the phase, we optimize the aperture to get rid out of the spurious phase jump. We came up with a novel automatic center search technique to locate the exact center. Rotate the ideal helical phase to match the retrieved phase, then the residual phase has been extracted. Showing three different kinds of compensation techniques. First is inline compensation, where we are adding a compensation phase with the hologram. In the pre-compensation, we first correct the input Gaussian beam and then generate OM, but in our method, at first we are generating OM and then correcting. Now I am showing the highlights of our work. You can see that the modal purity improved 35% with our post-compensation technique, which is higher than the conventional techniques. Also, we achieved more than 9 dB crosstalk suppression with our post-compensation techniques. We already discussed about the highlights of our works, and these are the